In a lab in Silicon Valley, engineers put two identical cups of water side by side inside the same metal box. Same chamber, same door, no divider between them. Then they turned the machine on, and one cup came to a rolling boil, while the cup sitting a few inches away stayed cool enough to drink. Nothing moved, nothing spun. The only thing that changed was where the energy was allowed to land. If you tried that experiment in the microwave on your counter right now, it would be physically impossible, and the reason why is the whole story. Because the box in your kitchen has been essentially blind since the day it was invented. It fires energy into a metal cavity and hopes for the best. It cannot see your food, cannot tell what's in there, and cannot aim. Stay with me, because by the end of this video, you'll understand exactly how American engineers taught a cooking chamber to see, why that one change quietly threatens the most common appliance in the country, and why, despite all of it, you still can't buy one at a normal price. Let's start with the machine you already own. There is no appliance in America more universal than the microwave. It sits in more than 90% of American homes. Dorm rooms, break rooms, gas stations, hospital wards, RVs, military barracks. Most people couldn't tell you the brand of theirs without walking over and looking. And almost nobody knows that the part doing the actual work was pulled straight out of a World War II radar set. There's something odd hiding in that ubiquity. The microwave is one of the only appliances people bought in enormous numbers and then quietly demoted. It was sold as a cooking device, full meals, roasts, cakes, an entire genre of cookbooks. Within a generation, most households had narrowed it down to 3 jobs: reheating leftovers, defrosting something forgotten in the freezer, and popcorn. Nobody decided that collectively. People just tried cooking real food in it, didn't like the result, and stopped. That downgrade is the clearest evidence that something about the machine was never right, and it happened so gradually that we stopped treating it as a flaw and started treating it as the definition of what a microwave is. The story is genuinely accidental. In 1945, a self-taught engineer named Percy Spencer was working at Raytheon in Massachusetts, standing near an active magnetron, a vacuum tube built to generate the microwave energy that powered Allied radar. He noticed the candy bar in his pocket had gone soft. Curious, he held popcorn kernels near the tube and watched them pop. Then he tried an egg, which exploded and splattered a colleague. Raytheon filed a patent application on October the 8th, 1945, for a method of treating foodstuffs. It was granted in 1950 as U.S. Patent 2-1-495,429. The first commercial product, the Radar Range, reached the market in 1947. It stood around 6 feet tall, weighed several hundred pounds, needed water cooling, and cost thousands of dollars at a time when a new car cost a fraction of that. Now here's the part worth sitting with. Everything since then has been miniaturization and packaging. Smaller cabinet, cheaper transformer, digital keypad, turntable. But the energy source at the heart of a 2026 countertop microwave is still a cavity magnetron, the same category of device those British and American radar engineers were building in 1940. We have gone from that decade to reusable rockets and pocket supercomputers, and the thing heating your leftovers still runs on radar hardware. So why does it heat so badly? To answer that, look at what actually happens when you press start. High voltage, typically in the range of several thousand volts, is fed to the magnetron. The magnetron converts that into electromagnetic waves at roughly 2.45 gigahertz, and those waves are dumped through a waveguide into the metal cooking chamber. That chamber is a sealed metal box, which means the waves cannot escape. They bounce. And when waves bounce back on themselves inside a reflective enclosure, they interfere with each other. In some places, the peaks line up and reinforce, creating regions of intense energy. In other places, they cancel out almost completely, creating dead zones with barely any energy at all. Physicists call the result a standing wave pattern. You know it by a different name. The reason your lasagna is molten at one edge, frozen in the middle, and rubbery at the corner. That pattern is not a manufacturing defect. It is the unavoidable consequence of flooding a reflective box with a single fixed frequency from a single fixed source. And here's the crucial detail. A magnetron has no idea any of this is happening. It is a one-way device. It generates energy at one frequency, at essentially one power level, and it has no capacity to measure what the food is doing in response. There is no feedback, no sensor telling it that the center is still frozen. It is an open loop, which in engineering terms means the machine acts without ever checking the result. Your microwave is not cooking your dinner, it is broadcasting at it. That single limitation created the second problem. Microwave energy heats by agitating water molecules inside the food, which generates heat from within, and that is genuinely fast. But the surface of your food sits against the cool air of the cavity, so the outside stays wetter and cooler than the inside. That is exactly backwards from every browning reaction a cook actually wants. Searing, crisping, and browning require dry, intense heat at the surface. A magnetron cannot produce that, which is why no microwave has ever made a decent French fry, and why frozen pizza and Hot Pocket makers have to laminate a thin metallic layer into the packaging. That layer is called a susceptor, and its whole job is to absorb microwave energy and get scorching hot so the surface of the food touching it can brown. Think about what that means. The food industry engineered a workaround into the box the food ships in because the appliance itself could never do it. American manufacturers spent decades patching around the flaw instead of fixing it. The turntable was added so food would rotate through the hot and cold zones and average out the difference. Rotating stirrers were placed near the waveguide to scatter the beam. Inverter power supplies were introduced so the magnetron could run at reduced continuous power instead of just switching fully on and off. Humidity and weight sensors were added to guess at doneness. Some models bolted on a grill element or a convection fan for browning. Every one of those fixes accepts the original premise: fill the box with energy, then compensate. Nobody was aiming anything, so a different question got asked. What if you stopped generating cooking energy with a vacuum tube from the radar era and generated it the way modern wireless equipment does, with semiconductors? That is the core of solid-state RF cooking, and it is the change that actually matters. Here's the mechanism. Instead of a magnetron, the oven uses power transistors, typically laterally diffused metal oxide semiconductor devices, the same family of amplifier chips that push signals out of cell towers, radar arrays, and 5G equipment. On its own, swapping the part sounds boring. The consequence is not. A magnetron gives you essentially one setting, on, at one frequency. A semiconductor amplifier gives you precise electronic control over three separate properties of the wave at once. Amplitude, meaning how much power. Frequency, meaning exactly where in the band you transmit. And phase, meaning the timing of the wave relative to another wave. That third one is where it gets interesting. Put two or more feed points into the chamber instead of one, then deliberately shift the phase between them. Where the waves arrive in step, they add together and you get a concentrated hot region. Where they arrive out of step, they cancel, and you get almost nothing. By changing the phase relationship electronically, thousands of times faster than any mechanical part could move, you can slide that hot region around inside the chamber without a single moving component. You are not spinning the food through a fixed pattern anymore. You are moving the pattern to the food. That is what let those 2 cups of water sit inches apart with only one of them boiling. Frequency control does something just as useful, and it's easier to picture if you think about the chamber as an instrument rather than a container. A metal box of a given size resonates better at some frequencies than others, and the moment you put food inside, you change that. A cold burrito and a bowl of soup do not present the same electrical load, so a solid-state system can sweep across a small range of frequencies, sample how well each one is being absorbed, and settle on the ones that actually deliver energy into the food instead of into the walls. A magnetron cannot do that. It sits at one frequency and drifts a little as it warms up, and whatever the chamber does with that is the chamber's problem. Then comes the part that changes the machine from a broadcaster into something closer to an instrument. A solid-state system can listen. Every time it transmits energy, it can also measure how much of that energy came back, unabsorbed, into the amplifier. Engineers call these forward power and reflected power. The ratio between them is a live report on what the food is doing. Water absorbs microwave energy very differently from ice. So does fat compared to lean muscle. When a frozen edge thaws, when butter melts, when a phase change happens anywhere in the load, the absorption signature shifts, and the electronics can detect that shift in real time and respond by retuning the frequency or redistributing the power. That is a closed loop. The machine acts, measures the result, and corrects. This is not a napkin sketch. In 2015, at its technology forum in Austin, Texas, Freescale Semiconductor demonstrated a working proof-of-concept solid-state oven called Sage, cooking steak with vegetables and potatoes in a few minutes in front of an audience. Freescale's engineers described the key advantage in exactly these terms. At all times, you know how much energy is going in and how much is bouncing back, so you know how much is actually being consumed by the food. That company was later absorbed into NXP Semiconductors, and the transistor technology it built went on to power other machines. One American startup, Wave, used a 250-watt solid-state module to build a battery-powered portable oven roughly the size of a thermos, originally aimed at soldiers cooking in the field. A magnetron cannot run off a battery in a device that size. A transistor can. And the voltage difference explains why. A conventional magnetron needs a supply in the range of 4,000 volts, while the transistors, in Freescale's concept, ran on a few dozen. Then a Silicon Valley company decided the electronics weren't the hard part, the software was. Markov Corporation, funded in part by eBay founder Pierre Omidyar, was awarded U.S. patents covering two ideas that fit together. The first, described in their filings as reflective energy steering, is the phase control trick I just described, deliberately shaping where the energy lands inside the chamber. The second is a control system that uses infrared and visual cameras to watch the food's surface temperature while it heats. The patent language is unusually direct about the approach. The feedback going into the controller can include visual light data, the surface temperature distribution of the item, or the radio frequency parameters associated with how the chamber is absorbing energy. And the filing describes training that control system with reinforcement learning, so the oven learns how a given item responds to a given action and plans accordingly. Put those pieces in one box, and the appliance stops behaving like a microwave. Their oven, called level, could identify different foods placed inside and drive each one toward its own target temperature simultaneously, in the same chamber, in the same session. Salmon to one internal temperature. Potatoes to another. No divider, no separate compartments, no second appliance. The company published a demonstration doing exactly that with cups of colored water to prove the energy steering was real and repeatable. And this same underlying shift is happening at a completely different scale, in a completely different part of the American food system, which is where the story gets bigger than a countertop. At Washington State University, a food engineer named Juming Tang spent his career on the exact problem that makes microwaves unreliable, the cold spot. In a kitchen, a cold spot means a lukewarm bite. In food processing, it means surviving bacteria, which is why, for decades, every attempt to sterilize packaged food with microwaves failed regulatory scrutiny. Nobody could prove where the coldest point in the package was, or that it got hot enough. Tang's team, with funding routed through the Department of Defense and the U.S. Army's Natick Soldier Systems Center, built a system running at 915 megahertz, a lower frequency that penetrates deeper into food than the 2.45 gigahertz in your kitchen, combined with a pressurized hot water bath and a carefully engineered path that moves packages through the microwave field. Then they did the harder work, proving mathematically and microbiologically how to locate that cold spot, measure it, and demonstrate the process kills pathogens. The first filing, in 2007, was for mashed potatoes, chosen precisely because it is uniform and simple. Federal reviewers spent 2 years on it. The FDA accepted it in 2009. Salmon fillets in sauce followed in 2010. In 2012, the USDA's Food Safety and Inspection Service issued a non-objection letter covering broader use in packaged low-acid foods. The technology was licensed to a Colorado company called 95 Labs, later acquired by the Indian conglomerate Tata, and in early 2026, the FDA accepted the first full commercial process built on the method. The practical result is a fish fillet that can sit in a pantry for up to 3 years with no refrigeration and come out firm and edible because it spent minutes in a controlled field instead of nearly an hour in a pressurized retort cooker being boiled into submission. Same physics as your microwave. Opposite philosophy. One floods a box and hopes. The other maps exactly where the energy goes and proves it. Quick question before we get to the part most videos skip. If a countertop oven could genuinely reheat leftovers evenly and crisp the outside in about the time your microwave takes, would you actually pay more for it, or is a $50 box that mostly works good enough? Drop your answer below. I read them. And if you like technology explained honestly instead of hyped, subscribing genuinely helps this channel keep making these. Now, the honest part, because there are real reasons this hasn't replaced anything in your kitchen. The first is brutally simple: money. RF power transistors cost far more per watt than a magnetron. The magnetron is one of the great manufacturing bargains in history, mass-produced by the millions, and it has been optimized for 80 years. Engineers in the RF power industry have said the quiet part plainly, that budget microwaves are going to keep using magnetrons. When your competition is a working appliance that costs $50 and sits in 90% of homes already, being better is not enough. You have to be better at a price people will actually pay to replace something that isn't broken. The second is power. Solid-state modules deliver relatively modest wattage each, so matching the raw output of a standard magnetron means using several of them, and every one adds cost, heat, and complexity to the power supply. The third is that the companies chasing this mostly aimed away from your kitchen. Markov positioned its oven toward offices and commercial food service rather than a consumer countertop. The first consumer oven to use solid-state RF came from a European luxury appliance maker at a price closer to a car payment than a kitchen gadget. Even the light-based approach hit the same wall. A California company called Brava built a countertop oven that cooks with 6 high-intensity halogen lamps that hit full power in under a second and can be zoned to cook different foods on the same tray, which genuinely solves the browning problem a microwave never could. It launched at around $1,000. And the fourth is that none of this is one invention. There's no single American breakthrough box you can point at. There is a semiconductor industry that made precise RF control cheap enough to try, a set of patents on steering and sensing, a university lab that spent 20 years teaching a regulator how to trust microwaves, and a handful of companies that got parts of the way there. That's how this actually happens. Slowly, in filings and pilot lines, years before anything shows up in a store. So no, your microwave is not going in the trash. It will probably outlive this video by a decade, but it's worth knowing what it actually is. It is a radar tube in a metal box, aiming at nothing, checking nothing, sold to you at a price so low that nobody has been able to justify replacing it. The engineering to do better exists. It's been demonstrated, patented, and in the industrial version, cleared by federal regulators. What's missing isn't the physics, it's the manufacturing economics. Which leaves a question I keep coming back to. The microwave survived not because it was good, but because it was cheap and fast, and nobody expected more from it. How many other machines in your house are sitting there right now for exactly the same reason? Not the best solution. Just the one that got cheap first and then stopped being questioned. Tell me which one you'd tear apart if it were up to you. And if you want more of this kind of thing, real engineering explained, without the hype, subscribe, because that's the whole point of this channel.